Good morning, everyone. Uh, Welcome to the last lecture of this summer school on artificial intelligence and machine learning. So far we have covered uh, linear regression, logistic regression, neural networks. We have seen some example of them. One tool which we haven't looked at up till now is convolutional neural networks. So convolutional neural networks are primarily used in 2D and high dimensional data. However, you can also use them for 1D data, and we will see in which cases convolutional neural networks are beneficial for us. Why would we need convolutional neural network rather than a typical simple neural network? So let's start. Sorry. Okay, so the slides are from Abhi Ruzgar, and they actually give an overview of all the topics. So let's start. So first, we would look at some introduction of convolution neural network as to what they do, how are they different. Then we'll see why can't we just use neural networks. Okay, neural network seems to work, as we have claimed that they are universal function approximators. They should be able to approximate any process, any phenomena. Why do we need something else? Then we will look at formally defining a convolution neural network. How are they implemented in practice? How do they look? Then some comparison, some disadvantages, and some application. Okay. So I'll give you, we'll start with a simple process. So we'll say, let's say we have an input image. Let's say this is 28 by 28. And we want to do alphabet classification. We want to classify an alphabet that's present in the image. This is exactly equivalent to the problem that we have done so far, where we classified digits, okay? So what would we do? With the tools that we have in hand, which is neural networks, linear regression, logistic regression, if I ask you guys to set up a machine learning algorithm which can learn the alphabet level of data, what would we do? We would probably set up a neural network, a multi-layer neural network, and give inputs, vectorized inputs of the image. So basically what we would do is say, okay, let's take this image, let's make a big vector out of it, okay? Where the first column comes here, the second column comes here, the third column comes here, and so on, right? So the size of this big vector would be 28 times 28, comma 1, okay? Then you say, okay, let's create a neural network, simple neural network, where maybe the first layer is 100 times 28 times 28. The second layer maybe is, how many alphabets are there? 24, right? 24 times 100. And this is, let's say, ReLU, and this is sigmoid, and that would be output. You would have, the network would output 24, a 24D probability vector, where each output component represent probability of belonging to that class. So this would be probability that the data is, that the label for the data is A. This would be probability that Y is equal to B, up till probability that Y is equal to Z. Of course, for the particular sample given X. Okay, everyone clear so far? Because this is the problem that we have already solved. We have done it with MNIST, right? Are there any questions? Okay, okay. So everyone is good so far. Now let me add something on top of it. Let's say that this image is not 28 times 28. Let's say this is 1,000 times 1,000 pixel image. Okay, and let's say that the problem is very complex and you would require, let's say, at least 10 layers or 15 layers to actually learn what is inside the problem. Now, what is the problem that we foresee? Let's try to set up a neural network, for a simple neural network for this problem. So what would happen? So the input x would be, the size of this would be 1000 times 1000, which is 10 to power 6, right? So it's 10 to power 6 times 1. This is the input of my neural network. Let's say that the first layer, W1, the shape of this is 100 times 10 to power 6. Remember, this has to match x, right? So now, just my first layer, how many components does this have? This has 10 to power 8 components. Just my first layer has 100 million parameters. Okay, that's already of the order of like the biggest convolutional neural networks in computer vision problems. And we have, it's just one layer. And we are using like a very huge downsampling factor. We are taking 10 to power 6 neuron and taking them to 100. Typically, it should be like probably not as low. This should be like 10 to power maybe 5 or 4. Then it becomes even more large. So do you see the problem? The problem is that if the input vector has large size, input image has large size, then you can get this problem where your network would be very large in terms of parameters. Does everyone see this problem? That if you have images which are high resolution, which have too many pixels, then you can get a problem where your neural network would become very large, very quickly. I'm looking at the chat. Is it clear to everyone? Okay. So this is first drawback of a neural network. Okay. So let me write it here. The first drawback is size in parameter space. In general, you can see that neural network can learn function of arbitrary complexity. If you have to learn something which can be separated by a layer, you just need a single layer neural network. If it's a combination of a few linear functions, piecewise, you can use a two-layer neural network. If it's, let's say, an arbitrary combination of piecewise linear functions, you can go to high-dimensional functions. So you can learn arbitrary complexity, depends on number of nodes and the number of layers. That's the property of universal approximation. But like we said, it might not be trivial. Your network might become very large size. Okay, this is the first drawback. Okay, this explains this with the example of 16 by 16 image, but the main idea is the same, that the number of trainable parameters can become very large very quickly. This is another important drawback. So simple neural network do not assume any structure on data. Okay, so basically, let's say this is your neural network. These are, let's say, input components. This component, let's call it component 0 and component 1. Neural network do not assume any relation between them. Okay, there is no relation between them. All of the weights between these components are learned independently. Now, what is a problem that can happen because of this lack of structure? One thing that can happen is, let's say you have this alphabet A, and let's say you moved it by a few pixels. Okay, if you moved it by a few pixels, let's say this A is now here. Okay, now in your data, in your training data, when you sampled alphabet A, this pixel was white, right? It's a white pixel, right? But now when you shift the image, this pixel become black. Now, if you look at this, let's say that this pixel, this corresponding pixel corresponds to this input of the neural network, okay? So if you look at how by a tiny shift of the image, how have the input changed? This change can be massive. So for example, this neuron has changed from, let's say, white was 1 and black was 0. So it has changed completely from 1 to 0. And remember that this is not just for one pixel. It's not the value of one pixel which has changed. A significant amount of pixel can change in this image. So if you do not assume any structure in the data, your input vector can change quite a lot by moving the images slightly. And this creates a problem because two very different input vectors means exact same thing. But since we don't have any structure in the neural network, we cannot enforce this constraint. So basically what I'm trying to say is that for the original image, let's say the X, this is the input, right? The original vector for this image. Let's say these are the pixel values, okay? Now, if you shift this, let's call it X shifted, this pixel, which is, let's say at location 0, it might move somewhere very different in the new vector. This pixel, which was here, this value, it might move somewhere very different in this vector. So small changes in the image produce massive changes in the input vector. Everyone understands this? Okay, perfect. So I'll give you like one example. Let's say that there are 16 columns and you move the input by one column to the right. This value, which was, let's say, at column row I, column J, now would be at row I, column J minus 1, right? Because the image has moved by one column. And if it has 16 columns, it would move 16 places. It would move, like, let's say this index was some arbitrary number. Let's call it index. It would move by 16 places. It would come to index minus 16 if we stack column wise. So values can jump quite a lot up and down if you move the image. Because of this, because there is no structure in neural network to tackle for this, there is no invariance to shifting, scaling, and another form of distortions when you train with neural network. Okay, now that's a problem because images can have a lot of distortions. For example, if I give you this is an A. If I give you this is also an A. If I give you this is also an A. If I give you this is also an A. But as we see that the input vector for all of these can change quite a lot. Now this neural network by default does not have any tool to learn these invariances. You can, of course, learn them through data. What you can do is you can say, okay, these invariances can exist in images and I want to learn them. What I'm going to do is I'm going to generate lots of samples which have all these distortions, and then I'm going to train my neural network with it. And that probably would solve the problem. That's true. But the thing is, the space of this distortion is huge. You would have to generate lots of samples. So let's look at a simple example. Let's say that this is a 16 by 16 image and binary image, two values possible, 0 and 1. So what is the total possible images in this space? What is the total number of images that I can generate on a 16 by 16 grid by using binary values 0 and 1? So image comes from a space of 0 and 1 to the power 16 times 16. So what are the total number of samples? It would be 2 to the power of 16 times 16, which is 2 to the power of 256. And I don't want to calculate it explicitly, but I can tell you it's going to be a very large number. So you would have to sample quite a lot. In order to exhaustively sample a space to train a neural network, there is going to be a ton of samples. So you cannot exhaustively sample it. You cannot generate all the samples, label them, and feed it to a neural network and ask it to learn these invariances to scaling, shifting, distortions, transformations and these kind of things. Everyone understand why it might be difficult to generate all possible samples of particular character. Okay. Okay, so now it seems like we are struck. Neural network do not learn these distortions by default, and we cannot ask the neural network to learn them from data because the data would become very large. So this is the second drawback. Okay, so this is explaining this point. So if you move the image, you can see that 154 input changes. 154 input pixel change their value completely. So it's like this vector, 156 values in them would flip completely just by moving it by 2 pixels. So this is huge. And remember, this has a total, it has just 256 pixels. So 154 out of 256 is more than half pixels. Okay. Sorry, it's 16 times 16. Yes. Okay. So what it means is that small changes, small imperceptible changes, can produce very large changes in the input vector of a neural network. If you use a strategy of stacking columns for an image, and there is a lack of invariance in the structure of neural network. If you want to learn this invariance, you would have to sample quite a lot, and it's very difficult to sample an image space exhaustively. Again, this you can see that this distortion can be from quite a lot of families. Okay. So the other thing is that it does not take into account any topology of the data. So what it means is that in images, data is quite structured, right? So for example, the value at 1 pixel can affect the value at another pixel. There can be some relation between these two because images have to represent objects. But neural network ignores these kind of topology, image topology. It looks at each pixel as some individual independent phenomena from all its neighborhoods. And because of that, a situation can occur where, let's say, you can, just by changing the value of 1 pixel, you can change the label of an image with a neural network because it doesn't look into this topology or structure of the image. So 3 major drawbacks we have identified: the network size, lack of invariance, and 3 is lack of topology, lack of input topology. So now let's see, how do we actually solve for these problems? Okay. So by the way, this is what I mean by topology. So for example, if you look at this pixel, if you look at the value of this pixel, for a neural network, the value of this pixel is exactly the same if this pixel comes from this image, or let's say another image where you have an A here, right? It's exactly the same for this neural network because it's just looking at the value of this pixel, and this pixel is black. But you can see that they come from completely different process, right? There is a completely different structure in the input. But neural networks cannot look at this structure. So we need some type of method which can look at this structure. Okay. So okay, so this is the suggestion that maybe we can use more data, but then it would produce a problem of more training time. Network size and pre-parameters would have to be increased to learn this complex process. So this brings us to convolutional neural networks. So convolutional neural networks are attributed to, again, LeCun and Joshua Bengio. I think LeCun was working at Bell Labs at that time. And they produced it for handwritten digits classification. So the IMNIS data, the image, the digits data that we have been working with so far, that's probably the data set that they used. And after that, eventually, convolutional neural networks have they are ubiquitous in computer vision problems now, they are everywhere. But they were introduced by Yann LeCun. Yann LeCun, I think, currently works at, he's the head of the Facebook AI research, I think. Bengio, if I'm not wrong, is at Toronto, University of Toronto. But these guys are known as the father of the field of modern deep learning, Joshua Bengio and Jan LeCun. Okay, so where did convolutional neural networks came from? Where is this idea? So they are inspired by human and actually primates vision. So when psychoanalytic experiments are done on human vision, it's observed that human vision has some sort of filters in the early layer of our visual tract, which respond to different patterns. So some neurons might respond to a pattern of oriented gradients in one direction, another might respond to another direction and things like that. So it seems like there is some sort of filtering, equivalent to filtering operation going on in our visual tract. And the other thing that's observed is that there are multiple. So if you look at biology literature, you would see that the human visual tract is like something like this. So here is the output word image. So there is like, it's called it level 1, level 2, level 3. I don't know the correct terminology for these, but there are like multiple layers of processing that happens in our visual tract. So there is the first layer, which look at low-level features like edges and these type of things. Then there is a second layer, a second level, which looks at complex features, maybe like shapes. And then there is third, maybe which looks at texture, and then fourth one, which looks for objects and things like that. So it's like a layered pattern where the complexity of the feature increases as you go down the network. Well, let's not call it network. When you go down the visual tract. Okay, so I'm going to skip this point because they are exactly the same as neural network. Let's see what is the difference. So systematically speaking, like if you want to draw a schematic for a convolutional neural network, you can break it down into 3 parts. So there is a feature extraction part of convolutional neural network, which extracts some features which are important to the classification task at hand. For example, let's say you are classifying a cat or a dog. Maybe we would want to look at the ears of the animal. So ears might be an important feature. Maybe we want to look at the whiskers and the nose and the tail. So features are these things. Important properties for the task. Okay. Then we have some layers in the neural network which introduce invariances. So by invariances, I mean that if you shift the image, because of this invariance layer, the output would not change. So this is to introduce invariances. We will see what each of these layers are. And once you have invariant features, you can simply learn to classify them. So this is for classification. Let's look at each of these in detail. Okay, so this is the topology of a neural network. So yeah. So first, let's see what is a convolution. How many of you have not heard of convolution? Can you just put like a yes in the chat if you don't know what a convolution is? Okay, you haven't heard of convolution. Okay, okay. So so there is a mathematical definition of convolution, and then I would stick to more practical definition from the perspective of machine learning. Generally, I'll just write it. So, for example, if you have convolution between x of t and w of t, this is from signal processing. This would be defined as integral from negative infinity to positive infinity x of okay, yeah, let's call it x of tau times w t minus tau beta. So basically, let me explain what this means. It means that if you have 2 signals, let's say this is signal 1, it's x of t, and you have another signal. This is, let's say, W of t, and you want to find the convolution. This is output y of t. You want to find the value of y of t, let's say at t equal to 10. So what you would do is, you would take this signal W of t, you would flip it, and then you would move it 10 points. This is tricky. Okay, so let's do it. Let's take this, let's flip this signal and move this origin to 10. So this would look something like this. Now this is at 10. Now you would take the product of the two signals, just simple multiplication, multiply each value of the signal with each value of the second signal and add them up. That would be the value of y of t at 10. Then you need to do it, of course, for all time values. So this is a bit complex. Let's look at a simple description which would help in our understanding of convolution neural networks. Let me get another slide. Okay. So what have we done so far to find the output of a single neuron in a neural network? So what do? Let's say this is x. X of 2 is, let's say, 10 rows and 1 column. Okay, and we have to find the output of one neuron. So this is x of t, and this is first neuron of a hidden layer. Let's call it Z, or let's say A11. How would we find the output of this? This would be W11, W12, W13, W14, and so on, right? W110. So basically what this A1 is, this is sigmoid of, let's say, W11 x1 plus W12 x2 plus W13 x3 up till W1. Let's make it 9-dimensional so that I don't have to write 10. 19 x10. Everybody understand this? This would be the output of a single neuron of a neural network, right? Okay, perfect. Now, what would be the output of a second neuron? You would have completely different values, right? Let's say that I want to do W21. This would be W21x1 plus W22x2 plus W23x3 plus W29x9. Okay. Now this is a problem because you have completely different values, weight values. I'm looking at these weight values for each output neuron. I want to suggest something like this. I say, okay, let's do this. Let's say that my x input vector is this, same, x1, x2, x3, x4, up till x9. But now I say that instead of having my weight vector, which is nine-dimensional, let's say my weight vector is 3-dimensional. Okay, so my weight vector is W1, W2, W3, and that's it. And now rather than multiplying it with all 9 values of my input, I multiply it with 3 values of my input at a time. So let's do this. Let's say that my A1 is the product of this with the first 3 values. Okay, so this would be sigmoid of W1x1 plus W2x2 plus W3x3. My A2 would be the product of this with the next 3 values. So this would be W1x2 plus W2x2 x3, sorry, plus W3x4. And similarly, my A3 would be sigmoid of W1 x3 plus W2 x4 plus W3 x5 and so on. Does everyone understand what's happening here? I'm taking a smaller weight vector and I'm multiplying it with each segment of my input. Okay, and of course I have to try all of them. I have to like take so in the first step I multiply it with 3, so this is this. Then I multiply it with the next 3, which is this. Then I multiply it with the next 3, which is this, and so on. You have to do it for all values. This is convolution. Okay, it should suffice for us that this is convolution. So when you take a vector and you move it along another vector, take element-wise product and add them up, this is convolution. Does it make sense to everyone? Okay. Okay, so we did it in 1D. You can very easily do it in 2D. Okay, so in 2D, you would move it along one dimension and then another dimension. So right now, my filter window is moving like this, right? This is my filter window, and I moved it in this direction. If you're working in 2D, and let's say this is your image, and this is your filter, you would move it in both directions, right? In this direction as well as the other direction. So let me show you how the convolution operation would look. Yeah. So you can see that I have this is my filter, and I just move it on my image, take the element-wise product and add them up. And that's my output value for a filter. Everybody understands this? Everybody understands the convolution operation? If there is any confusion about convolution operation, please ask. We can have a look at it. We can try to. Again, let me just make it clear that this is not the formal definition of convolution, but this is just from an understanding perspective, this is exactly what happens in a convolutional neural network architecture. Okay, so if everybody is clear about convolution, let's actually look at what convolution does. Why is it helpful? So let me get, okay, let's see. So basically what the convolution neural network does, what these filters, this 3x3 patch, by the way, this thing, we call them filters. Okay, these are filters. They look for certain properties in the image. And let's see how do they look at these properties. Okay, so a typical convolution neural network architecture would look like this. Lower layers would look at some properties like maybe edges or something like that. Some higher level would look at some corners, and then even higher levels would look at like shape patterns, and eventually you would be able to classify. So basically, if you look at the output here, you would see that it generally look for edges, oriented edges. Maybe if you look at here, you would see that it looks for corners. And if you look at here, you would see that it probably looks at shapes and so on. So as you go deeper in the network, you learn more and more complex features. So let's see how does filter actually looks for patterns in the data. So let's come here. So let's say that you have an image, any image, which is, let's say, like this. It has values zeros here and values 1 here. Okay, and you want to find places where there is an edge. So basically, you are interested. You want to find these pixels where there is an edge, where your value become light to dark as you go from left to right. Okay, what I suggest, what I say is that okay, you can do it if you convolve it with this filter. So this is a 2x2 filter, which has zeros here and ones here. Okay, and let's see how this would happen. Okay, so if I want to find the output of my filter at this pixel, what should I do? So this is my output. Okay, let's call this X, let's call this W, and let's call this Y. So if I want to find the value of Y at this pixel, what should I do? Come on, guys. So I should just take this filter and place it on top of image at this pixel. Okay, take the element wise product and add them up. Does it make sense to everyone? Okay, so I'm going to make the problem a bit easier for myself. I'm going to say that this is not 1 and zeros. The values are not ones and zeros. The values are 1 and minus 1. And we will see why this is helpful. Okay, we have values 1 and minus 1. So what is the value of the image for all these 4 pixels? So I'm going to write the values of image here. Image value is 1, 1, 1, 1, because all the 4 pixels are bright, right? So this is X. I'm going to put it a tilde on it just to say that it's a patch in the image. And what is the values of my filter? My filter is this, right? So it has values, sorry. So it has values 1, 1, minus 1, minus 1, right? Everyone agrees this far? Okay, so now let's take element-wise product. If I take element-wise product of these two, I would get 1, 1, minus 1, minus 1. If I add them up, I'll get 0. Okay, so the output at this pixel is 0. Okay, let me find the output at this pixel. Okay, if I want to take the output at this pixel, I'll get the patch at this pixel, image patch, X tilde, and image patch at this pixel is minus 1, minus 1, minus 1, minus 1, because all 4 by 4 values are inside this negative region, right? What is my filter? My filter is 1, 1, minus 1, minus 1, right? If I take the element-wise product, this would become 1, 1, minus 1, minus 1, 1, 1. If I add them up, I'll get 0. Is it clear? So the output at this pixel is 0. And I can see actually that the output at all the pixel in this region would be 0 by the same logic. And similarly, at this region, it would also be 0. Now let's look at the pixel right at the boundary. Let's look at this pixel. So the X tilde at this pixel, the patch of image at this pixel would be 1, 1, minus 1, minus 1, right? Because this is your patch. So 1, 1, minus 1, minus 1. And what is my filter? My filter is 1, 1, minus 1, minus 1. If I take the element-wise product, I'll get 1, 1, 1, 1. I add them up, I'll get 4. So that's exactly what we wanted, right? So now we see that at the boundary, you have the values are 4, 4, 4, 4, 4, all the way down to 4, and everywhere else the values are 0. So what this filter is doing, it's looking for edges, horizontal edges. Are these horizontal edges? Vertical edges. It's looking for vertical edges, right? Does everybody see the magic of filtering? That you can look. So basically, essentially, what you're doing is you are looking for a patch which looks like this. Everywhere in the image, if the patch looks like this, you give it a high value. Anywhere in the image where the patch does not look like this, you give it a low value. So you can look for any particular type of pattern that you are interested in. Let's say you are interested in looking for this patch in the image. let's say this patch, just convolve it with this filter. If you convolve it with this filter, it would look for this patch. You can look in image for this patch. Just convolve it with this. Wherever this patch is present in the image, you will get a high value. And wherever there is a patch which looks different from this image, this patch, you would get a low value. Everybody understands this? Okay, perfect. So now the first part of our convolution neural network is done, which is feature extraction. So I'm sorry. So feature extraction is basically looking for certain type of features in the image. And now we have seen that we can look for any feature in the image, any feature that we decide we are interested in, we can create a filter for that feature and look for that feature in the image. Now let's look at the second component, which is getting invariance, getting some sort of invariance in the image. Okay, I'm going to come here and I'm going to say, how do we learn invariance? Okay, so the simplest thing that you can do is you can think of, if anybody who is from electrical engineering background, you can do some sort of low pass filtering will get you some sort of invariance. So basically, what do I mean by this? So let's say I'm given a patch, okay, in which images can move slightly, images can be distorted slightly, different things can happen to this image. But I want to get a property on this image which is like invariant, which does not change much on this patch. What if I say that rather than looking at the values at each pixel, I can do something like taking the average value of a patch. So basically, let me explain what I mean by this. So let's say this is an image. This has an alphabet A in it. And now let's say the alphabet A moved by 1 pixel to the right? So my new alphabet is maybe like this. So if I look at the two images at each pixel location, they would be quite different because the pixel values have changed. But what if I say, okay, let's not look at the pixel value only. Let's look at some local average of, let's look at the average value of a patch, like a 2x2 region in an image. So I would see that if I do that, it would be the difference between the two images would be less. So basically think of it as, rather than looking at the image, you look at the smooth version of the image. You smooth the images and then you look at the smooth version of the images. And we can see that it would actually remove the difference between the two images, because let's look at the simplest example. The simplest example would be if I rather than having an image, I take the average value of the image. So the average value of both these images are same, right? Approximately same, because what is the average value of the image? You take all pixels in the image and divide it by the total number of pixels. Okay, so if I look at the average value of image 1, so let me do it. So average value of the green is summation of all pixels divided by the number of pixels. And similarly for the first image, the red image, it would be summation of, let's call it x tilde, xi's divided by the size of xi. And this value would be same, or almost same for both images, because the number of black pixels in both images are same. Black pixels are the pixels which are taken by digit A. Everybody understands this, what I'm trying to say? Is that rather than looking at the value of the image pixel as a feature, I can look at the average value of the image as a feature. And if I look at the average value of the image as a feature, it's not changing when you move the image. Is it clear to people? So I'm going to, just to make it a bit clear, I'm going to extend on it a bit more. So let me say that this image is 8 by 8, and the number of pixels which are contained by. Are you looking for average of the whole image or just by region? The whole image. I'm looking at the extreme case where I'm looking at the average of the whole image. Okay, so I have an 8 by 8 image, and let's say the number of pixels which are covered by digit A are 20. Okay, so what are the total number of pixels in this image? The total number of pixels in this image are 64. What are the dark pixels? Dark pixels are 20. So dark pixels are 20. What are the number of white pixels? The white pixels are 44. Okay, this is for the red image. What would it be for the green image? Again, it would be same. The total number of pixels is same. The dark pixels are also 20, and white pixel, of course, the rest of the pixel would be white, so it would be 44. Even for let's say I distort it quite a lot. I make it this. I move it all the way to the right. Even for this, the total number of pixels are 64. Dark pixel are 20, and white pixels are 44. So what would be the average value for all three of these images? So let's look at the average value for the blue. This would be 44 divided by 64. This is a number, right? I'm converting an image into a number where the number is the average value. What would be the average value for green? It would be 44 divided by 64. What would be the average value for the red? It would be 44 divided by 64. And now we have an invariant property. You can move the character anywhere in the image, and this number would not change. This number would remain same, right? So this is how we construct invariant features. We can do some sort of local aggregation, local pooling, local averaging. Everybody understands how I got this invariant property on this image. I converted the image. I say, okay, I won't look at the image. I would look at the average value of the image. And the average value of the image would not change if you move the digit anywhere in the image. Even if you change its size, it would change, but it would not change very fast. Okay, compared to the input vector, it would change very slow. If it is a colored picture, the background has other colors, not white or black. Yeah, of course, it would be a little tricky in other cases. But again, even if it has like a colored RGB values, if you move the image slightly, only one column would change, right? All the other columns would remain the same because you're moving the image. So still the average would be much more stable compared to the pixel-wise values at each pixel location. This can be done, right? You can have invariant property, but there is a drawback to this. The drawback to this is that you lose all the topological information of the image. So what do I mean by this? So the value 44 by 64 is the same. For example, if you have this as an image, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, and 20. So if you look at the average value for this image, where you have just individual pixels, dark pixels in the image, this would also be 44 by 64. So that's a problem now, right? Because you lost all the information about your alphabet, right? Because any random 20 pixels in the image would give you the same answer as your invariant feature. So what do? We say, okay, we will adjust these two information. We would go somewhere in the middle. We would say, let's not take average on the entire image. Let's take average on a patch in an image. Okay. So what we do is we say that we take an image, okay, and the output would be the average value of the image in this patch. This would come here. Okay. Then I'll take the average value of the image in this patch, and it would come here. Then I would take the average value of image in this patch, and it would come here. Then I'll take the average value of image in this patch, and it would come here. And you can, of course, repeat it for the rest of the image. So basically, you downsample the image and take the average in a small patch rather than take the average of the entire image. So it would have the best of both worlds. It would have some invariance, and it would have some topological properties of the image as well. So does everybody understand this balancing act between keeping the properties of the image as well while getting some invariance as well? Everybody, is this operation, this invariance generation operation clear to everyone? Rather than looking at the values of image at a pixel, you look at the values of image in a patch. And this would change much slowly as you change the image compared to the image values, image pixel values. Is it clear to everyone? I need to see some yeses in the chat so that we can move. Okay. Okay, so this is called average pooling operation. Okay. You can do similar to average pooling operation, you can do max pooling. Max pooling, look at the maximum value on a patch. So you look at this patch and you select the maximum value and put it here. So same operation, same idea, but rather than taking average of all the values, you take the maximum of all the values in a patch. Okay, and that's it. These two tools, we have all the tools that we need to define a convolutional neural network. So convolutional neural network typically are like this. So you have an input X. Again, X is an image now. You have a convolutional layer, conv layer, which does the filtering that we saw first. Then you have some non-linearity, maybe ReLU or sigmoid. Then you have a max pooling operation to get some invariance. And you repeat this block maybe a few times to get higher level features. So this is conv, this is non-linearity, this is max pooling, and so on. You can do it multiple times. Now, let's say after this is layer 1, layer 2, you did it for 5 layers, 5 blocks. You would have a set of features here, right? Now you want to classify them. In order to classify them, we use the exact same setup as a simple neural network. So we take these features, we make a big vector of them, and then give it to a simple neural network to classify. The difference is that this thing it has important features and it has invariance properties. Okay, so you take an image, you extract features from it which are invariant, then you put them in a big vector and you classify them with a neural network. That's the architecture of a convolutional neural network. Is it clear to everyone? Okay. So with this, let me show you some. I'm going to skip this. It's good that you look into these slides. You would find some important information there. But I'm going to just quickly show you some network that we're going to work today. This is Lenet. This was introduced by LeCun to classify digits. And it has a convolutional layer, then a max pooling layer, then another convolutional layer, then another max pooling layer. And finally, it has 2 linear layers. Linear layers, by the way, this is a neural network. This is a simple neural network. This is a conv layer, convolution layer. This is a max pooling layer. This is another convolution layer and another max pooling layer. we will construct it exactly. We will construct this network today. We'll change it slightly. Our input would be 28 times 28. So it would change the number slightly, but I would explain it as how to do it. So some things to notice before we actually implement it. So let's say this is an image and your filter is, let's say, 3 by 3. Okay. Okay. And let's say I want to find the output at this pixel, at the very pixel at the very edge of my image. If I place my filter on top of it, I'll get something like this, right? Does it make sense, right? I've taken my filter and put it on top of this pixel. Now, if I want to take element-wise product, how do I take element-wise product at this pixel? Because image value is not defined at this pixel, right? Does it make sense to everyone why I cannot find the filter value at this pixel? Because I would not have information at this pixel. So typically when you take convolution for an image, you have to drop some pixels around the boundary because you cannot find the value of the filter at these pixels. If you take the filter on top of this pixel, the filter would have an overlap with a region from outside the image. So if your filter size is, what would be a nice notation for this? Let's call it L and R. Generally, L and R are same. So L equal to R equal to, let's call it F filter size. Then you would lose F minus 1 divided by 2, where this is integer division. You would lose these pixels around the boundary. So for example, in this case, 3 minus 1 divided by 2 is 1. So you would lose 1 pixel around the boundary. If your image is 18 by 18, the output would be 17 by 17. Does it make sense to everyone? The output of the convolution operation would be 17 by 17. Is it clear to everyone? Why the output size of the filter operation is slightly different from the input? Okay. Okay. Is there any confusion for anyone in this? Does anybody want me to explain it again? Okay. So with this, let me show you some examples on Lenet. So basically what you can observe in these slides is that these are the output of the layers of the convolutional neural network. So this is the output of the first layer. This is the output of the second layer. This is the output of the pooled operation, the feature, which is input to the neural network. And you can see that as the digits are changing, the output of the first layer and the second layer are changing. First layer is changing the fastest. Second layer is changing slower. But the output feature, the invariant feature, is changing the slowest. We don't want invariant feature to change because we don't want it to change as we change the input. Particularly here, you can see that you can change 4, you can rotate it, translate it, but this does not change. It changes when you change the digit, which is what we expect. We want it to change with digit, but we don't want it to change with rotation, translation, scaling. And you can see it with scaling, it doesn't change much. With the rotation, it doesn't change much. With translation, it doesn't change much. So it is indeed an invariant feature. You can have even like different type of transformations where you put different noise on it, you stretch it, you make it thicker, and this feature does not change, which is very nice, which is exactly what we want our network to learn. Everybody sees the motivation of how we generate these invariant features from a neural network. You use two operations, you use convolution, you use max pooling. And the composition of these operations gives you a feature which would not change much with your transformation. Is it clear? Okay, so with this, let's look at some code. Let me see if there is anything else. Okay, I'm not going to go through comparisons. You can look at these things at your own time. Let's go to some code and write a simple convolutional neural network. Okay. So before we do, let me, everybody can see my screen, right? Okay, so I have, Okay, so if I go to the course instruction page, you will see the what we have to do at the end of course tasks. So the end of course tasks are the following. First, all of you has to okay, why does it say course project? I'll change it. It's course survey. So everybody has to fill in the course survey. I will be collecting emails, so I would know that who hasn't filled it and who hasn't filled it. If you haven't filled it, I'll send you a reminder. So you have to fill it. Everybody has to fill this. It will collect your email. I will suitably anonymize it. So feel free to write anything. We will not know who gave what review. We will just know that who has given it and who hasn't given it. So please, everybody has to do it. It will take around 2 minutes. I would, after I explain things, I would suggest you take 2 minutes and do it before we start the lecture. I'll give you guys 2 minutes to go through it. You have to submit your homeworks and your projects. Again, they would be in the zip code, in a zip file. I will send you the access code in an email. I don't want to put it on a YouTube video, so I don't want people to send me random stuff. So I'll give you guys the access code in email. So just put in the access code. It will ask for your name to record. It will record your name, and then you can just drop your zip file here. So let me just let's see if it's okay. It's good. So if you provide the access code, it will bring you here. You can just enter your name. And then you can just drop your file here. Okay. So simple, easy to upload stuff. You can do it. Again, I'll give you the access code for this as well. You will enter your name and you can drop your file. Okay. So with this, let's take a 2 minutes break. Um, just go through the course instruction page, go to the course survey. It should say course survey, not course project. But anyway, go to this link and fill in the survey. I'll stop sharing my screen for 2 minutes, and then I'll come back after 2 minutes and we will resume our session. Okay, but please do it, and we'll see you in let's make it 5, not 2. So it's 10:03. We will resume at 10:08. Okay, so we are just writing the conv layer, the convolutional network. We initialize our layers, and now we are writing the forward pass. Okay, so our input image is of size 28 by 28. We have a convolutional filter layer of size 5, which means that we would lose 2 pixels on the left, 2 pixels on the right, 2 pixels at the bottom, 2 pixels at the top. So what would be the size of x1? 26 times 26, it actually would be 24 times 24 because you're losing 2 pixels on either side. Okay, so this size would be 24 times 24. What should I do after this x1 layer? I need to do some invariance layer. And how do we do invariance? Which layer do we use to get some invariance in our convolutional neural network? Max pooling, right? So we need to do max pool in 2D. And I think it would be like this. It would take in an X and it would do max pooling in a region of 2 by 2. Okay. Okay. So the input is X1. By the way, for my linear thing, you can just override the variable, call it X, X, X. But I want to keep track of X1, output of the first conv layer, output of the second conv layer, because I want to plot it just to show you guys how it looks. Okay, so that's why I'm storing them in separate variable. Okay. So what would be the size of X after this? So after I do the max pooling, what would be the input size was 24 times 24, and I am doing max pooling in a 2 by 2 patch. So what would be the output? So each 2 by 2 patch would be converted into a single pixel. Okay. So what would be the output of the shape of the output of the max pooling layer? So you just divide exactly 12 by 12. This would be 12 by 12 because each 2 by 2 patch is converted into a pixel. So you divide the number of rows by 2 and you divide the number of columns by 2. Yeah. So now I can just copy this thing. And let's call this x2. And this is conv2. This is x2. This is x. So what would be the shape here? You would lose 2 pixels on the left, 2 pixels on the right, 2 pixels at the bottom, 2 pixels at the top. So input is 12 by 12 of shape 12 by 12. You lose 2 pixels on each side because you have a 5 by 5 filter. What would be the shape of the output? I'm looking at the chat for your answer. It would be 8 times 8. Thank you. And what would be the output after the max pooling? It would be 4 times 4. Right? Okay. So now at this point, x is, the size of x is 4 times 4. And you have 50 such channels because this is the output channels, right? So you had 20 input channels and you have 50 output channels. So you have such 50 channels and 50 channels. So if I want to stack these channels, all 50 of them in a big vector, the output shape would be, if I, let's say, if I stack x in a vector, it will be 4 times 4 times 50 by 1. Everybody understands this? I take all 50 of these channels, vectorize them, and store them in a big vector. This would be my feature, which would go into my linear layers in my simple neural network. So the shape of my first linear layer would be 4 times 4 times 50. Okay. Everybody understands where I get this number, 4 times 4 times 50. I have 50 channels. Each channel is of size 4 by 4. If I put it in a big vector, the size of my big vector would be 4 times 4 times 50. Is it clear? Okay, perfect. Now, after this, we just need to pass it through the linear layers. So we will say f dot prelude and self dot linear 1 x and x is equal to f dot prelude self dot linear 2 and x. So this is the simple neural network. We have a 2-layer simple neural network, which takes in this feature and gives us the output. So that should pretty much do it. Let's define a net. So we'll call it net is equal to my net. And do we need to give it anything? No. So let's see if we can. Let's see what the errors are. Okay, we don't have anything. Okay. What have I called it? This is conv1. Sorry. Okay. Is it fine if the final layer is not sigmoid? Yes. In this case, the final layer would not be a sigmoid because it's a multi-class classification problem. the loss that we would use, it would first pass it through the softmax layer and then do the loss function. So the cross entropy loss function inside PyTorch does the softmax as well as doing the cross entropy loss. So that's why we did not do the softmax here. We just return the raw value. Of course, I have to return it as well. Return x, and let's return x1 and x2 as well, so that we can see the output of the first layer and the second layer as well. Okay, so now we have the network. Let's try to set up an optimization problem. Let's try to set up a learning setup for it. So let's get a learning rate. Let's say that it's 0.01. Let's get an optimizer. So optimizer would be optim dot, we want stochastic gradient descent, and the parameters are net dot parameters, and the learning rate is LR. What else? We don't need to do anything. Let's write some number of epochs for this. So I'm going to call it underscore epochs. This is the number of iterations that you want to give it. Epochs. And then we have to do for each batch train loader. So we have X and Y, where X is batch 0 and Y is batch 1. Let's set up a device so that we can do everything on CUDA, on GPU. So device is equal to torch.device 0. Let's take everything to the GPU. Okay. Now let's take the data. We can do it here. This is the same step from yesterday. I'm just taking all the data in the network to my GPU. Then I pass the data to this, and I'll say my loss is f dot cross entropy. I'm assuming that it should be this. I'm never quite sure of the order. So input is tensor and then target. So I think it's this. Okay, and then we have to clear the optimizer buffer. So we have to do optimizer dot zero grad. Zero grad. Then we have to do loss dot backward. This takes the backward pass, and then we have to do optimizer dot step. This take a step in the gradient direction. Let's calculate the full loss. So total underscore loss is equal to loss dot item. So I want to calculate loss at each iteration. So at the beginning of the iteration, I'll set the loss to 0. Then I will add the loss of each batch to it. And this, I create an empty list and I append this loss to this list at the end of each iteration. And then I do some lot of this just to make sure that everything is running. So in the beginning, let's just give it 1 iteration just to make sure that everything is fine, and then we'll give it 10 iterations. See how it goes. Okay, so what is the problem? Invalid value and column this. So let me just, to make sure that everything is in order, let's put it to CPU. And let's see what the mat1 and mat2 cannot be multiplied. Okay, so there is a problem with one of the layers. So let me just make sure that the shape is fine. Okay, so let's look at the shapes of my data. Okay, so it's 28 times 28 indeed. So let's come here. The number of input channels is 1. The number of output channels is 20. The size of my filter is 5, and this is 1. Then it takes 20. Output is 50 channels. It's 5 and 1. This is 4 times 4. To me, it seems fine. But just in case, I will do this. Say print x1 dot shape. In fact, let's just print x dot shape. To do x1, just so that we see what is the shape of my data and where there is a problem. I have a feeling that the problem is in one of the linear layers. Let me just make sure that both linear layers are the same size. Okay, so it's 500 and then 500 to 10. Should be fine, but let's see. Okay, so the input channels, okay, y is, okay, 20, then it's 50, and probably need to make it a bit more readable. So let's shape after on one this. Okay, so shape after on, okay, pool one is this. I have to just make sure that I have the correct syntax for pooling. I think it might be, I think this, I think I have used incorrect syntax for pooling, but let's just double check it. After conf 2 is x2 dot shape, x dot shape, and x, okay, this is x. 2 is this, and shape after linear 1 is x. Okay, so after conv 1, the shape is 24 by 24. After pool 1, it is 12 by 12. After conf 2, it's 8 by 8. After pool 2, it's 4 times 4 times 50. So it should be fine. Oh, I've made a silly mistake. So you remember we did this thing where we said that in PyTorch it uses a different convention than what we do. The data is stacked along rows. So it's the shape of the linear layer is the output channels times the input channels, not input channels times the output channels. Okay, so I'm assuming that's the problem. So it's probably this. 4 times 4 times 50 and 10 star. It's 500 and this would run now. Okay, this seems to be a bit strange. Okay, I'm sorry. I'm sorry. I have to, so after I've calculated X, I have to adjust its shape. So I have missed this. I have to do this. X is equal to X dot view. And this is -1. I don't care about the data points. All I care is that this has to be 4 times 4 times 50. Okay, let me just double check that I'm giving it the correct thing. This probably previously it was correct. The number of input, the number of output, the number of input, the number of output. I think this is correct. Okay, so now position 1 must be tensor, not tuple. That makes sense because I'm not inputting just logits. I'm inputting two other things, which is y1 and y2. The input of the first output of the first layer, first conv layer, and the second conv layer. Okay, so now everything is fine. Let me stop it, remove the print commands, and then run it. Yeah, so let's remove all these print commands. So this has a good debugging practice. So for me, at least prints still are like a very good debugging tool. Helps me quite a lot. Try to find where mistakes are. So since I have disconnected the runtime, I might have to run these again. Okay, so it seems to be running fine, which is good. Let it complete the first iteration and then I'll give it 10 iterations and we will see how it goes. While it's running, there are any questions, any confusions about what I did, please feel free to ask them. I'm doing it on CPU. I have to take it to GPU. But let it run. Let it run for one iteration, and we will take it to GPU. By the way, this thing, CUDA 0, your machine might have multiple GPUs, right? And then they are like tagged by 0, 1, 2, some sort of names like this. So this means give it to the um, first GPU. It is the problem with PLT. Let's see, ls. Okay, ls is empty. And why it is empty? Oh, sorry, this is loss, total loss. Okay, so let's give it 10 epochs. In fact, let's give it 5 epochs. I don't want to train it completely. I just want to show you that it can be trained. Then you guys can use this notebook and train it completely for yourself. Okay, so any questions? We have, it will take like minute, 2 minutes while it's running. Let's discuss some questions, anything. You will have, by the way, from 11 onwards, 11 till 1, you have time to work on your project. So I will be here and available in the chat. You can ask questions here. You can reach me through email as well. For example, you are doing some project and you set up some code and it didn't work and you need some help. Send me an email and I'll try to help you guys. Try to finish it by the end of the weekend, like before Monday, or maybe by the end of day Monday, but don't delay it past that. And don't go for something too complicated. You can have some simple application of linear regression or logistic regression or neural networks or convolution neural networks. Okay, so it's working. I'm going to train it for 10 iterations and see how it works. Then we'll look at we'll look at its accuracy and see how accurate it is. And we'll look at some intermediate layers as well, output of some intermediate layers. In fact, because we have done the code for accuracy yesterday, I would be more interested in looking at some intermediate layers. So let's let it finish the code and then we would see how to plot some intermediate layers, output of the intermediate layers like conv1, conv2, and see how it looks. Okay. Let's make the time count. Ask some questions, guys. If there are any questions, I'm looking at the chat. Or give me the overall thoughts about the course. How was it? Did you guys like it? How difficult? The most important thing is how difficult it was. Was it too difficult for our project to record our voice for the presentation? Preferably, yes. It's good that you record your audio. But if, let's say, in some case you cannot do it and you just want to give the presentation, that would work too. But I prefer, like, because I want to hear you guys explain what you have learned or what you have implemented. So that would be great. So PowerPoint allows this very simple tool of recording a presentation. So you record a presentation and record your audio on the background. And it should be short, like 3 to 5 minutes. It does not need to be terribly long. And I just want to hear you guys explain the process of tackling a machine learning problem so that I can see how much you have gotten from this course and how familiar you are with the tools. For RGB image to reset all channels, or is it better to convert the image to black and white? No, RGB you can stack all channels. You don't need to stack anything, in fact, because you would use convolutional layers, and convolutional layers you can give the number of input channels 3. So when you start, you give it the input channel 3, and it will take care of everything. So you don't need to stack anything. The stacking would be done at the level of the feature. Once you get the feature, you would stack it. Okay, so learning seems to have worked quite well. Let's look at some intermediate output. So let's see what I can do. I can do something like this. I can say for batch in test loader. Something like this. If I is greater than 1, great. Which is enumerate. We will enumerate the batches in this. You can, of course, plot it for multiple batches. I just want to look at the first batch. And then what do? We can say for j in range of batch 0 dot shape 0. I want to do it for all data points in the test loader, all data samples in the test loader. And what do I want to do? I want to get the data, so X and Y, and this would be batch. Okay, so I want to extract the JF sample from the data. So this would be, okay, let's do it like this. Let's first extract the batch. So I'm just extracting the data from my batch. After the data is extracted, let me extract the image from it. So image would be X, the jth component of X, and this. Now let's pass it through the network. Y1, Y2, net IN. Okay, and should I just do it for one sample, because this would generate too many figures. So let's do this. So it's greater than 1. Great. So we will just do it for one sample. Okay, so let me do it in a smarter way. Let's remove this. Let's do this. This. Okay, so now I have the output for the entire batch in Y hat, the intermediate output in Y1 and Y2. So let's look at Y1 and Y2. So the first component, the features for component 1, let me call it feature underscore on 1. For the first data point would be Y1, right? I'm just taking the feature for the first data point, and let's call feature underscore on 2 for Y2, the first data point. And now let's plot these. So I can do something like this. Let's get a figure in range of feature shape 0. What do I need to do? So how many features do we have? We have, in the first layer, we have 20 features. So sorry, I need something like PLT subplot, 4 rows, 5 columns, and I plus 1. And then I just simply plot, I'm sure, feature underscore font 1, I component this. Hopefully this would work. Let's see. Cannot convert CUDA. Okay, so I have to do this. detach CPU, and maybe .numpy as well. So I have brought the data, I have removed it from the backward pass graph with command detach. I bring it back to CPU with .cpu, and I bring it back to numpy with numpy. Okay. In fact, let me not do it here. This can create some problems. Let me do this, and let's do it here. So let's copy this. So y1 is equal to y1 this, and so I'll just make y1 and y2 numpy variable. Can we just use, I think it would not work. It would still say that you cannot do any operations on it. So it's better to detach it. So this is the output of the first layer. This is how they look. Let's plot the output of the second layer as well. So this would be this. And we have 50, so I'll say 5 and 10. So let's run it again. Okay, this is 2. Okay, so these are the outputs of layer 1, and these are the outputs of layer 2. So you can see that the first layer is just like some simple operation on the image. It's like a blurred image, edges of the image. So you see this is an edge, right? This is an edge. These are edges. And because the filter is 5 by 5, it's not very sharp. It's a bit blurred. But you can see that the second layer now has like some more interesting thing. These are like some patterns. They don't look like the number. If you go deeper, you would see that these are like, so this might be always active when there is like a edge in a horizontal direction. This might be always active when an edge is in the vertical direction. So think of it as like small pieces of image. So it's basically breaking the image into small pieces. And if, for example, an image has this piece and this piece and this piece, then it's maybe like a 5. If an image has this piece and this piece and this piece, then it might be a 4. So you can see that features are becoming more complex as you go down the network. Does it make sense to everyone? How do I get these intermediate features and how do I plot them? Okay, okay, okay. So at this point, I will stop the lecture. This notebook is shared with you. You can access it through the website. Let's go through the end of course instructions one more time because I will stop the lecture. We will not have a lecture after this. I will be available in the chat to answer any questions. So basically,